Okay, so in this video we're going to have a look at an application of the dominated convergence theorem. The dominated convergence theorem is a really powerful result from measure theory that says if a sequence of functions converges in a measure space and fn's are measurable functions, that means if some set is measurable, then f inverse of that set is measurable, and it converges pointwise to a function f, and the fn's are dominated, so f sub n is less than g for some function g, then the integrals of the fn's converge to the integral of the f. So you can see how this might kind of be useful, for example, when you want to interchange limits inside an integral. So this says if this is what the limit on the outside, this one is the limit on the inside. So that's what the dominated convergence theorem lets you do. And the problem we want to solve is to show that the integral absolute value of f minus fn d mu tends to 0 as n tends to infinity. So the way we're going to do it is we're going to use the dominated convergence theorem. So we want to satisfy the two properties. The first is this one, and the second is this one. The first property is that we want this f minus fn to converge to some other f. So we're going to call this, because we want to kind of use the dominated convergence theorem on it, so we're going to just name this a new function. So let's call it h. Okay, h sub n is equal to the absolute value of f of n, and we're gonna call the limit h, and this limit is going to be 0. So first of all, we're going to show that this is true, that hn tends to h. And so the way we're going to do this is we're going to subtract f from both sides of this thing. And we're allowed to do that because of the algebra of limits. And so if we do that, then we get that f sub n minus f tends to 0. So if something converges to 0, its absolute value must converge to 0 as well. So we can just take the absolute value. And now this is h. And this is equal to hn, because we're allowed to just switch these two around because it's absolute value and the negative sign will disappear. So we have the first property, that h sub n tends to h, which is the first property we need, except that this is written with an f. Okay, now we want the second property, that these hn's are bounded. That turns out to be also pretty straightforward. We have that from this convergence by taking limits on both sides. Well, g is fixed, it doesn't depend on n, but this f sub n, it tends to f. So at the limit, we have that f absolute value of f is less than g. If the absolute value of f is less than g, then we can use the triangle inequality on this, and this is less than or equal to the absolute value of f plus the absolute value of f sub n. But the absolute value of f is less than g, and the absolute value of f sub n is less than g, so this is less than 2g. And this just says we need any function, so 2g is some function, and so we have this h sub n. Well, we need to take the absolute value of it. Actually, it doesn't make a difference. We'll do it anyway. The absolute value of hn is less than 2g. So we've satisfied the second criteria as well. We found a function that bounds the f of n's. So hn now converges to 0 dominatedly. And that means we can use the dominated convergence theorem. So we can now substitute hn into this part, which will give us this, and h into this part. So let's do that. So substituting hn into here, hn is just this part, so we get integral of absolute value of f minus fn d mu. This tends to the integral of h d mu by the dominated convergence theorem. But what is this? Well, h we said is 0, so this is the integral of 0 d mu. But the integral of 0 is just 0, and so we're done. Thanks for watching. See you next one.